Hello everyone, welcome to this talk about the paper Semantic-informed driver fuzzing without both the hardware devices and the emulators. This is joint work with Kang-Jie Chu Shiwu from University of Minnesota and Yong Qi from Xianjiao University. Today I will talk about the device-free driver fuzzing. First, let me show our motivation. Linux and its various distributions are widely used, like Ubuntu, Arch Linux, and so on. They are used in cloud computing, audio devices, notebooks, and mobile phones. In Linux, 17% of the kernel code is related to device drivers. The left picture is an output of LSHW command on my computer. Many hardware devices need their drivers to support roaming. Device drivers are critical to the security of the system, and they run at the same privilege level as the kernel. If the driver is compromised, the attacker can control the entire system. However, drivers are more vulnerable than other parts in the kernel, and studies have shown that the driver vulnerability density is 3 to 7 times higher than the rest of the kernel. This is mainly because drivers have higher requirements for developers and insufficient driver testing. More importantly, drivers have a larger attack surface than other parts of the kernel. As this picture shows, compared to other parts in the kernel, in addition to the traditional attack between user space and kernel space, the driver may also be attacked by malicious hardware, so the drivers have a larger attack surface. In recent years, some attackers have used USB ports and Thunderbolt ports to obtain root privileges of the operating systems. This is done by exploiting vulnerabilities in the drivers. Fuzzing is widely used to find and fix vulnerabilities recently. Fuzzing uses invalid, unexpected, or random data as input to a program, triggers different paths and runtime, and uses checkers to monitor unusual behavior and runtime for vulnerabilities. Developers ensure the security of program and runtime by fixing vulnerabilities. Currently, driver fuzzing relies on the hardware devices or corresponding emulators. In fact, the operating system supports a lot of devices. For example, there are more than 13,000 PCI devices in Linux. Buying these devices and operating them will cause high costs. At the same time, the emulator can only emulate a part of the device. For example, the commonly used kernel only emulates less than 130 PCI devices. So it is impossible to fuzz the complete driver with the emulator. Therefore, to enhance the kernel security, we need device-free driver fuzzing. Is that feasible, and how to do that? To know if device-free driver fuzzing works, we first study the characteristics of device drivers. After study, we found that the development of device drivers follows the Linux device driver model. This model is tree-like, and the node representing the device, which contains two important data structures. One records various data information of the device, and the other records the various operations supported by the device. The device driver presents a two-stage workflow. Stage 1 is the initialization centered on the device structure. The kernel needs to construct the device structure. Stage 2 is the communication between the driver and the device. Through a study of driver characteristics, we found that in order to successfully initialize the device driver, we must make the driver to successfully construct the structure required by the device driver. So the question is, can we make the kernel to build these structures without the hardware? There are two challenges to constructing the required structures. The first is the complexity of the data structures used in the device driver. Take the net devices structure used by the network card as an example. It contains 114 fields, and its size exceeds 2,000 bytes. Filling such a large input space with random input is obviously impossible. The second challenge is addressing diverse I/O devices. There are many ways for the kernel to interact with the device. The commonly used I/O port, MMIO, and DMA. These methods have a large address space. It is therefore difficult to determine what input is required to enter the current address. To make the kernel construct the required structure without hardware device, we need to overcome these challenges. Fortunately, in our previous study of driver characteristics, we found that during the driver initialization process, many validations must be successfully passed, and these validations form an input validation chain. For example, the right side is an execution path of the kernel to initialize the driver, and there is some validation information on this path, such as whether there is a device, whether the manufacturer is correct, whether the corresponding driver is provided. Only through these validations are successfully passed, then the device can be operated successfully. Such an input validation chain gives us a lot of semantics. So our basic idea is to use the semantic information from the driver's code to support them. According to the above analysis, it can be seen that the driver itself contains a lot of semantic information to get driver initialization. So from the intuitive, we can use this semantic information to help the kernel build the required structures. Let's explain it by analogy. When I see this socket, we know that the first plug does not match the socket, and the second one can be matched. We can think of the driver and this socket, and the device as the plug. So our basic idea is to use the semantic information from the driver's code to support the device-free driver fuzzing. According to the basic idea, we propose FUZZ, which is a device-free driver semantic-informed fuzzing system. The whole system mainly consists of two parts. One is a semantic-informed mechanism, and the other is a fuzzing framework. The picture shows the components of FUZZ. The semantic-informed mechanism is the core of the entire system. It is because of the semantic-informed mechanism that we can solve the two previous challenges and do the device driver fuzzing without the hardware device. I will briefly talk about the semantic-informed mechanism. The core of the semantic-informed mechanism is to extract the semantic information of the driver. Here we mainly propose three new techniques. The first is a byte level and field-sensitive value inference and mapping. The second is Byte-Priority Inference. The third is pass state as feedback. The first technique is for inference of some constant values in structures. The second is inference of some variable values, mainly splitting multiple bytes of the variable into single byte inference. The third is to get the fuzzer by feeding back the state of the driver execution error to the fuzzer. The fuzzer generates the next suitable input. The first technique contains two parts. One is value inference, and the other is the mappings of value and address. Let's take a look at value inference first. When doing value inference, we first identify the I/O-related fields and build an I/O dependency graph. We first use data flow analysis to collect data structures related to I/O, and then further determine key fields by judging whether input has an impact on the control flow. On the basis, the I/O dependency graph is constructed. Then we collect the constraints in the validation chain through the I/O dependency graph. There are two constraints, C1 and C2 in this figure. Through these constraints, we can know that when accessing a certain address of the device, the value that needs to be returned is 0x808615df. After the value inference, we also need to know the address corresponding to the value. The figure shows the code of the PCI device combined into the address, where bus is the bus address, FN is the device address. These two addresses are determined when the device is mounted. Since REG is some predefined macro, we can get the value of REG through data flow analysis. So we can deduce the actual address. And therefore, we can establish a mapping relationship between fields and addresses. With the value information of the previous fields, we can infer what the expected value is when accessing an I/O address. Of course, there are still some dynamic mappings that need to be handled. You can get these details from our paper. The second technique is Byte-Priority Inference. This technique is to infer variable values in some structures. The basic idea is to reduce the mountain space that the fuzzer needs to search for input by splitting a multi-byte value into multiple single byte values. As the figure shows, when a device is read, the kernel obtains the value of AABB. It is difficult to generate this value directly by using the fuzzer. However, since AA is used first, mutation of AA can be prioritized during fuzzing, which can reduce input search space. Here we just show the temporal validation chain pattern. We found that the validation chain follows a specific temporal pattern. First, the code execution starts with the device read. The read gets a value V from the I/O address. Second, the value V will then be used as a source operand and a bit mask for bit operation to generate a new intermediate value, I. Third, this value, I, will have validations before the value V is used. Fourth, the value is used. In this execution pattern, the value V is read in advance, but it is referenced subsequently. Therefore, when fuzzers provide device input for current address and next running, it should mutate the part covered by bitmask first, then validation, uses, and so forth. Back the states of the driver execution error to the fuzzer. The driver code enforces a large number of sanity checks against the inputs and the internal operations. If a check fails, the driver will handle the failure. Therefore, error handling in the driver is extremely common. The most common way of handling failure is to pass an error code as a return value upstream. We observed that such error codes can serve as helpful feedback that indicates the current plan execution stream. That is, based on the return value, the fuzzer can know if the input triggers an erroneous execution of a normal execution. It's useful because it tells if thus has generated the bad value in our inputs correctly. For example, and the finger shows the different places where the execution failed means that the input that need to be mutated is different. And showing the finger, the first execution failure means that the input corresponding to C1 is incorrect. And the second failure means that the input corresponding to C2 is incorrect. This information will infer the fuzzer which put caused the execution to fail. To feedback this state, we first collect the locations of all driver functions that can be return errors. These marked locations are used to send the feedback to fuzzer. Then we insert a stub before these marked locations. This stub is a small piece of code with a special VM call. At runtime, when the driver enters the error state, the driver code will call the VM call instruction which causes the system to exit. DRFuzz notifies this behavior to the fuzzer. The special VM call takes a parameter that contains useful information for the state analyzer. This parameter can indicate whether the input meets the expected value since the last mutation, and the state analyzer uses this parameter to hint at the byte-priority mutation to improve the mutation for the next input. We implement DRFuzz based on LLVM, syscaller, and QEMU. Specifically, we use LLVM to perform the semantic analysis and the implementation. We implement the semantic-informed mechanism based on the syscaller. The implementation complexity is shown in this table. We evaluate DRFuzz. This shows our evaluation environment. Considering the large number of drivers, we randomly choose 10% of device drivers of each bus. Then use DRFuzz to test whether drivers can be discovered and enabled without the hardware. We allocate a time bucket of 24 hours for each driver. DRFuzz successfully triggers the execution of the probe function for all drivers. DRFuzz further successfully initialized the 149 drivers without a success rate of almost 7%. We also collect the accumulated code coverage in the driver-related code. The code coverage after testing 214 drivers have reached 5%, compared to the 3% without DRFuzz. That is, DRFuzz increased the coverage by 6.7%. After a successful initialization, we can also use our semantic-informed mechanism to generate semi-malformed inputs to improve the code coverage and the throughput of driver fuzzing. DRFuzz achieve a fuzzing throughput range from 21 to 33 executions per second, much lower than the fuzzers for user space program where fuzzers often achieve up to thousands of executions per second. However, driver fuzzing is generally slow. In fact, DRFuzz outperforms existing driver fuzzing in throughput. To compare with the syscaller, the average throughput is actually increased from 24.2 execution per second to 28.7 executions per second. The main reason is that the feedback of error states execution effectively accelerates the fuzzing program. The main reason is that the feedback of error states execution effectively accelerates the fuzzing process. Overall, in this research work, we implemented DRFuzz, which is a system that fuzz drivers without a device. Our main contribution here is that we study the characteristic of device drivers and give some interesting characteristics, and then we propose a semantic-informed mechanism in which we propose 3 new techniques. We have shared our source code here. If you are interested, you can access it. That's my talk. Thank you, everyone.